Okay, so thank you so much for coming out here on this cold Saturday morning. And as Lance was telling you, after California, I came here and I thought, who in their right mind stays here for longer than a few years? And I know that, now I know who it is. It's people like me who were not really in their right minds. But anyway, I guess one of the things that you do notice every year is that there's this sudden change in temperature and all of a sudden there's no football, tennis, all that sort. But the good news is that there is a lot of fun that you can have in this cold world. And that's what I'm beginning to discover, and what I would like to tell you about, what I'd like to share with you is some of the fun that I've been having here, and both in terms of the world that you see around you, and also the mysteries of a low temperature world and if you think this is cold, believe me, it's going to get way colder as far as that little guy here goes that I'll show you in a second. So when you do go to really cold temperatures, nothing like this, way, way, way colder, you see some rather mysterious phenomena coming out. And so what I'd like to discuss with you today is both what it means for something to become cold, what are the changes that you see in the world outside you, and what are the changes that you see in this mysterious low temperature world that you will get a glimpse of today. So the one thing that I'd like to ask you is, you've all been brave troopers, you've come out here, and really one of the things that we really should do is not only learn physics, but have fun in the process. And so one thing I'd like from you is your enthusiasm, and anytime you have questions, just raise your hands and I will try to answer those questions, but also if you have comments along the way, those are most welcome too. So let me begin by asking you, you all know that it's time to gear up for the winter. One of the things that I'd like to ask you is, what are the changes that you're noticing right now? Be brave, just... Anybody? Yes? Less activity outside, absolutely. And what is going on outside? Snowing, yes. Runny noses, well, I'm not going to talk about that today, though I could speak from experience. Anything else? What are you doing at home to make sure that it's not the same as it is outside?
Turning up the heat.
Yeah, turning up the heat. What was that? Exact, sleeping in, I love that one, yes. Okay, so there are a lot of changes that you see going on, and one thing that I'd like to talk to you about today is really even ask, what is the concept of temperature? What does that really mean? And that's something that we're going to discover, but before we get started with all that, let me actually start with something absolutely dramatic, okay? So here you see a door, and you see that it's frosted up a little bit. Anyone have any thoughts on what this might be? Louder, louder. Yes, absolutely. How many of you have actually seen liquid nitrogen before? How many of you want to see it again? All right, okay, so this is a totally fun liquid, okay? And you can see it's pretty dramatic, okay? And this is at really cold temperatures. I mean, the temperature that you are at right now is nothing compared to the temperature that this is at, okay? And one of the things that you notice is that things that are actually in liquid nitrogen undergo an extremely dramatic internal change, okay? That's something that you'll see right now. And for example, this lettuce, I guess, cabbage, thank you, sorry. Once your head is freezing, you really can't think straight even. So if you look at what happens when you actually put this cabbage in liquid nitrogen, cabbage is soft and chewy, it's a good vegetable, but, well, it didn't completely crackle. Flowers are even better, okay? So if you look at these flowers, take a bigger one, okay, take a bigger flower. Oh, in the bigger door. Okay, we have lots of liquid nitrogen today. Okay, so if you look at what happens with flowers, I can actually hear this liquid nitrogen boiling. I can hear some crackling, and probably the flowers are more dramatic. Okay, so it completely shatters. And instead of doing that to all these beautiful flowers, I will just go on with the next thing and maybe give it to the lovely ladies here, okay? So, because I don't want to do that to all the flowers, but if, you're welcome. But if you want to come here after the lecture, we can try doing it with whatever's left, preferably cabbages, not flowers, okay? Okay, so what I'd like to show you now, so this was giving you a sense of how a lot of different structural changes actually happen when you go to lower and lower temperatures. Some things you don't even have to go to that cold of a temperature. You know that water, for example, freezes at 0 degrees centigrade. What I do want to tell you about is that I told you that there's this absolutely mysterious world at very low temperatures, and what I want to demonstrate to you is exactly what's going on in that world, okay? So the phenomenon that I'd like to tell you about today, so a lot of the things that you saw, for example, this, it's relatively dramatic, but it's no surprise. You could have done this at home, though I don't advise it, okay? But it's not something which is absolutely surprising. Now, the thing that will be pretty dramatic that you probably won't be able to do at home is what I have here for you, okay? So what I have here is that's a little piece of a compound called yttrium barium copper oxide, long fancy name reflecting its structure. Never mind the fancy name. What is important about the substance is that it undergoes a very dramatic transformation under low temperatures. So what I'm going to do is I'm going to put some liquid nitrogen on this. We'll talk about liquid nitrogen and what it means in a little bit. And wait for it to cool down. So it takes about a minute or two for it to cool down, okay? And we can observe what happens. You can see it on the screen there. And it usually takes a lot of liquid nitrogen. Anyone know what this substance, anyone know what's going to happen to this? Louder? Ah, okay. I'll get to that in a second. And okay, one person says it's going to start floating, okay? And the other person says it's going to create a magnetic field around it. Both of these are, yes. Well, actually, this in particular won't start floating. Something will start floating. Anybody else have any ideas as to what's going to happen? Yes? Yes. And this is the lesson that I want you to take home today. And as a consequence, what both of you are talking about, this thing with the magnetic field and this thing with the flotation, all that will actually pan out. And you'll see this in a pretty dramatic way, okay? And so what you're actually going to see is that thing there is what's called a superconductor. And really, that's the theme of today's lecture. I'm going to tell you what a superconductor really means. We're slowly going to build our way up to that. But what's really dramatic is that I'm telling you that right now, it's undergoing a pretty dramatic transformation. Just by looking at it, you can't tell. But what you can do is look at what happens when other materials come close to it, specifically when you have this magnet coming close to it. It's a little magnet that you'll see on the screen more clearly. Anyone know what actually ends up happening? It floats, it levitates, it hovers above this superconductor. Okay, so if everything works, we should be able to see that. Do you see that? Okay, so it's pretty dramatic. It's actually levitating a little. Is that actually levitating? Is that in its best? Yeah? Okay, okay, okay. So, well, it does a lot of that too. But the really neat thing about this is that you can start it spinning sometimes. So you can see, that it can actually spin over the superconductor. So keep an eye on that once in a while, and actually, if you see that dropping, just give me a sign, raise your hand or say it dropped or something like that, because then we'll discuss that physics too. Okay, those of you that are trying this through yoga, I wouldn't advise going to these cold temperatures, okay? All right, so what I'd like to tell you about is really, at the end of the lecture, if we can understand what's going on with this substance, then we would have actually learned a lot, because you'll actually be learning about a completely different state of matter that you don't usually get at room temperature or even in the coldest temperatures that winter might bring you, okay? Any questions so far? Questions are really welcome. Questions, you know, talk, well, not disruptively, but you know. So anyway, so, oh, actually, do we have a pointer? Here we go. Okay, so we've already looked at superconductivity. I told you that it's a remarkable low temperature phenomenon. It's one of the things that I study in my research, and it's one of the things that's actually slowly gaining more value for its applications, and it's definitely something that in the next, you know, few years, people will start to learn about more and more, and it's something that I want to tell you about today, okay? But in doing that, so it's going to be a story. It's a story, it's kind of a mystery novel that will unfold. What is the secret behind the superconductor and its levitational powers? Okay, so this is the kind of mystery story that we have unfolding here today, but I want to go over it step by step. There's a lot of physics that one needs to understand to really be able to understand what that superconductor is doing. Okay, so what I'd like to tell you about today is when we keep saying low temperature, we have to understand better what low temperature even means. Okay, so first what we'll do is we'll start discussing the concept of temperature. And then what I want to tell you is that everything that you saw here, the shattering of the cabbage and the flowers, the superconductivity, and also what you told me about snowflakes, all that, all these are wonderful examples of a phenomenon called phase transition. And so I'll tell you a little bit about what this phase transition actually means, and then I'll take you on a journey through this kind of low temperature world, and in particular, we'll look at what happens with superconductors. So just keep in mind that when we're talking about magnetism and things like that, to really understand what's going on in this material, you really need to look at what the constituent particles in the superconductor are doing. What are the constituent particles? What is all matter made up of? Atoms. And what are atoms made up of? Louder? Yes. Perfect. Protons and neutrons and electrons. And by the way, feel free to scream it out. It's fine. If you look at a metal, this is a harder one. If you look at a metal, what is responsible for the conduction that you see? If you put a wire and you turn a switch on, what is causing the conduction of current in these wires? Do you know? Electricity is right with electrons. Perfect. Okay? So really, what's going on here, and what one really has to understand is to understand, you saw here, which you don't see here that dramatically anymore, you really have to understand what the electrons inside the superconductor are doing and what it is that's causing them to, what it is that's causing the magnet to levitate. And that's what we'll look at the end of this lecture, and hope that will secret of this levitation for you. Okay? Questions? Questions are always welcome. Okay, in the next hand is one question. Yes! Okay.
What was that
Oh, you want to write down the call? Okay. The short form is YBCO. Okay? So that's, and usually, okay, this thing is, believe it or not, it's a high temperature superconductor in the sense of the original superconductors, you had to go to really, really low temperatures. Those could be any of your usual metals. This one is special. It's called YbCO, and the full form is yttrium, barium, copper oxide. Okay, so that's the full form. Other questions? Okay. So let's move on and really let's ask, if I'm telling you about the low temperature world, we really have to get a sense of what temperature even means. And so let me tell you that most of what we measure is really measured in, well, actually, let me ask you, what are the units that you measure temperature in? Kelvin, wonderful. Okay, go ahead. And anything else? Oh, thank you. Oh, my Lord. It has dropped. Okay. Okay. So this means it dropped. Thank you. Thank you for letting me know. Back to room temperature. That's what's going on. Okay. What are the other scales of temperature? Maybe somebody else. Celsius. And then we have one more. Fahrenheit. Okay. So these are all different scales of temperature, but in a sense they're measuring the same thing. And really one that is most common when you're studying all these different phenomena, not the room temperature that we're used to, is something called Kelvin, okay? And Kelvin is something that we need to get used to. So why is Kelvin important? The reason that Kelvin is important is that this is something which, zero, when you're actually looking at 0 Kelvin, that can be much lower than that, okay? So that's the important scale. But just to give an idea of what Kelvin even means, 0 degrees Celsius. Water freezes. Exactly. Water freezes. Celsius, for example, is 273 Kelvin. So if you have Celsius, if you have degrees Celsius, just add 270 to that and you'll get the scale in Kelvin. So that gives you a sense of what this Kelvin scale is all about. Now, for this whole talk, let's actually think in terms of Kelvin, okay? And look spectrum of that occur in the universe, okay? So if you look at the whole universe, now this scale, a compact scale that you have here, it's rectangular, okay? So you have absolute zero here, and that is that you can almost never achieve anywhere. If we look, you know, ice melts, somewhere around here, that's about Kelvin, that's where we are sitting at. So we are sitting in this tiny, tiny range out here. And if you look at the scale here, it's not 1, 2, 3, 4. It's actually 0. It's actually 1, 10, 100, 1,000, 10,000, 1 million, etc., all the way up to billions of temperatures. So this, I mean, degrees Kelvin. And this is something really remarkable because if we're trying to study the universe, it's not enough to confine ourselves to the world that we're used to. There's stuff going on at really high temperatures. Hot stars, the inside of hot stars, for example, can go up to 1 billion Kelvin, okay, which is really, really high. So there's this range up here, and for example, nuclear explosions, unfortunately, at very high temperatures. They're 1 million Kelvin. So the energy, for example, released in a nuclear explosion is just unimaginable. It's unimaginably higher than anything that we're used to, okay? Now, those are the high temperatures. If we come down here, this is what we're going to study today. These are at lower and lower and lower temperatures, okay? And if you look at the lowest temperatures that we have, it's about nanokelvin, okay? And this nanokelvin is actually an extremely small, tiny, tiny number. And it's actually 1 divided huge number, reasonably small. Just compare that to where we are sitting. We're just sitting out here. And if we really want to go to the coldest, it's really low. Okay. For today's talk, we will be able to go to somewhere around here. Okay, so that's how low that we can go with liquid nitrogen. Okay, so this gives you a sense of the kinds of temperature range that you see in the universe, okay? And now the question is, what is temperature? How do you actually define temperature? What does it mean? And now your answer to that and we'll explore that in a little bit. And you know, once you tell me what your answer is, I'll tell you what my thoughts are on that. So what is temperature? When you sit here and you say, this room is warm, when I go outside, cold, why do you feel that way? Okay, this is great, we're gonna, okay, because, louder? Okay, exactly, that's absolutely correct. Anyone else have any other interpretations or comments to add to that? Okay, so both of these are correct, and they're perfectly right, okay? And maybe should we look at the Brownian motion? Yeah. Okay, so essentially, it's exactly that. When you look at temperature, it's actually, you know, intuitively you have some idea of what the temperature might actually be, but in reality, it's something that's a little hard to grasp. In fact, it is something really hard to grasp, and what both you told me is the closest that we can understand, you know, as far as a mental picture goes in our heads, okay? What's really going on is that if we look at the air molecules around here, they're actually moving extremely fast, okay, super, super fast, and they're hitting us. They're hitting us at tremendous rates, and, you know, if you actually had some image of the way these things were coming and hitting you, you'd be pretty horrified, okay? And so really what's going on is that you have the random motion. The randomness is really important, and it's the random motion of these particles, air particles, that's actually defining the temperature in this room. And one of you said average kinetic energy. How many of you have heard of kinetic energy? Okay, excellent. Most of you have heard of kinetic energy. Roughly speaking, that Kelvin scale that I told you about measures the kinetic energy of the particles. So if they were moving at 0, if they weren't moving at all, that would be 0 Kelvin. Okay, so that means 0 Kelvin. It doesn't have to be only air molecules. For example, if I look at a piece of metal and I say, why is this hot versus another piece of metal may be cold, there too, it's the random motion of the atoms or whatever it is. They're jiggling around, and the hot metal actually has more of these thermal motions, as it were, and the cold metal has much slower motion of particles, okay? Okay, now the other pretty amazing thing is that you can actually change the motion of these particles. And in some, okay, anyone have any thoughts on how you can change how fast these particles are moving in this room, for example, or in a little container? Apply heat, that's a great way. You can actually put it underneath, and what that does is it actually draws heat from the external, from the exterior, and that gets these particles to move faster. Okay, so that's what's going on. That's one way of doing it. It's usually a foolproof way of doing it. What is another way? Yes? You can also apply pressure. So both these are actually really excellent ways of doing it. And so let me just show you a little demonstration that you see here, okay? So this is a gas of molecules. And what I can do is, for example, I can change all these different controls. You can change the volume. You can change the pressure. All these are different ways of having these molecules move faster. And in fact, so for example, let me change the volume here. Okay, if I change the volume, you can see, are these going slower or faster? Slower or faster? Okay, let me just do something really drastic. Compare that, okay? And actually, I should say that the pressure is remaining fixed to that. Okay, when I'm smaller, are they moving slower or faster? Slower. Okay, so they are moving slower, but it's very important that I keep the pressure fixed. What I'm doing is I'm keeping the pressure fixed. The pressure also comes from these molecules. These molecules hitting against this piston actually causes the pressure, okay? And so what you can see is that as I make the volume smaller, these are moving slower. To actually understand that takes a little more well, I'll have to explain it to you. You can ask me after the lecture. Important here is that you can see that changing the pressure of the gas, for example, actually, or the volume of the gas can change the temperature of the gas, and we can actually do the same thing, for example, in this room. If we had a way of changing the pressure, we could actually change the temperature. Where is an instance where this is used pretty regularly? In fact, there's some things that you see in the world around you that use this principle to work. Refrigerator, that's absolutely right. Refrigerator, so essentially engines of all sorts work that way. And those of you, for example, who are interested in cars, if you wanted to study the way the engine works, it really depends on all this physics of changing the volume, changing the pressure, applying heat, because really when you look at your cylinders, how many of you have heard of cylinder engine? Okay, so you've all heard of that. These cylinders actually use these same kind of principles where you have gas in a chamber and you can change all these properties and change the temperature, pressure, et cetera, and extract work that actually gets your car running. Okay, now this kind of random motion has a name, and this was one of the things that Einstein was famous for observing, the name of this kind of random motion. Let me ask someone besides the young Einstein we have sitting there, okay? Else? Okay.
Brownian motion?
Is that what you were going to say? Absolutely. Okay, so this sort of movement is called Brownian motion, and in fact, this was one of the things that Einstein, believe it or not, was well known for. What were other things Einstein was known for? Photoelectric effect. Else? Atom, yes, and the atomic bomb, a sorry history which rectified, but yes, all these things are things that Einstein was known for, but actually when he was 26 years old, these were the two things that he did, two of several things that he did study, namely the photoelectric effect, you can ask me about that later, but also the random motion of these particles. And the thing is, we can't really see the random motion because obviously the air molecules are too small, but what it has done for us is, can you see these particles here moving around? Barely. You can do? Okay, there we go. Now that it's dark. Can you see these slowly drifting along? How many of you can see that? Okay, great, but I can't see you. But no, but that's great. So all of you can actually see that. And I mean, this is a pretty remarkable example of Brownian motion. What's going on is that Erica actually blew some smoke into a little gas chamber. So essentially, the smoke, in a sense, the smoke particles act as little markers. And the reason that they're drifting around is that you have the air molecules that are hitting them and buffeting them around and actually giving rise to this thing called Brownian motion, which is a completely random motion, okay? By looking at the motion, by looking at how fast these particles are traveling, you can also get a good idea of the temperature of that gas chamber is, okay? Okay, so this is what temperature is all about, and now but how do we actually measure temperature? When I look at this and I say, oh yeah, I can tell you what the temperature is, I'll sit here and calculate, figure out how fast they're going, tell you what the temperature is, but before that, one of you will come and say, oh no, wait a minute, I have an easier way, and you'll tell me the temperature immediately. How would you do that? How do you usually find the temperature of anything? Thermometer, exactly, okay? So the thermometer is a really good way of looking at the temperature of anything at all. Another way, if you, for example, looked into outer space and you saw all those stars sitting out there and you said, I wonder how I can tell the temperature of a star. Now this is a real one. How do you tell the temperature of a star? Louder? Color, is that what you said? Absolutely, okay? So one way of telling the temperature of something is by looking at its color, not like the orange sweatshirt or the green sweatshirt, okay? That's not what I'm talking about. If you look at really, really hot objects like stars, you actually look at the color that these are emitting, and by looking at the color that these are emitting, you can actually tell what the temperature is of that particular thing. Now, all of us, in fact, all of us are also emitting some kind of radiation. It's just that it's a radiation that you can't normally see, okay? And I'll talk about it in just a second. But just to demonstrate for you, if I look at this, I actually have a light bulb here, okay? And let me turn it very low. Okay, and I'm not going to make this very high. What color do you see? Red, exactly. And as I change the temperature, or as I put more current through it, what color is it becoming? Orange, yellow, and then I'm not going to go any further. Essentially, as you keep raising the temperature, you actually find that it goes red to orange to yellow to what else? White, because all the colors are coming, but if I looked at what the colors are made of, what's the next color? Green, blue, etc., etc. So this is what's called black body radiation. And for example, I can do the same out here. Some of you said white. The reason that it's white is that all the colors are getting mixed up. But if I look at the primers here, I can actually look at the whole spectrum of colors. This at very low temperatures. I'm increasing the temperature, and you can see these faint red lines. You can barely see these faint red lines, but it's primarily red. As I keep increasing the temperature, other colors come in. Actually, I find that it becomes more and more blue, and if I were to increase the temperature even more, it would actually end up being completely blue and then violet, okay? So what's important is that a lot of objects, us included, tell the temperature that they're at by actually, you can tell what temperature they're at by actually looking at the radiation that they're giving out. And this sort of thing is called black body radiation, okay? And what it tells you is that all of us, and this black body, I'll explain what that means in a second, give out some kind of radiation, and by looking at the radiation coming, you can tell the temperature of that particular object. The black body refers to something which can radiate perfectly without any disturbance, okay? And anyone know what kind of radiation we are giving off? Yes, infrared, okay? So some of you might have actually seen, for example, of polar bears in the snow. How many of you have looked at infrared photographs? Some of you have looked at infrared photographs, and you know that, for example, if you want to spot a polar bear in the snow, it's usually impossible, but take a photograph of the guy in infrared, and he comes out as this big blob, okay? And the reason is that all of us here, actually devoid of what our skin color might be, are in the infrared. And so this is the kind of black body radiation that we are giving out. Now, the higher the temperature, the more we go towards the beautiful colors, and then the more we go towards the ultraviolet. So if you look at stars, if you look out in the sky and you see a red star and a blue star, which one has the higher temperature? The blue star, okay? So if you look at a star, you have a blue star. The red star actually giving off most of its long wavelength at a short wavelength, and you can tell that it's the blue star that has higher temperature. Same with the flame. If that the flame is blue, you'll know that usually that's a higher temperature, okay? What else? Okay, so this is as far as temperature. Now that we have, oh yes, by the way, a very, very strange thing happens when you look into outer space. So what is our temperature? What temperature are we at? Not her, is that, yes, exactly, and in Fahrenheit it's 98. Now if we look in Kelvin, it's close to room temperature. Now if we look at stars, let's say we look at the sun, what color do you usually draw as? okay? And that's actually pretty accurate. It actually gives you the color. The color is pretty accurate. It gives you the right temperature. Any thoughts on what the temperature of the sun might be, of the sun's surface? 20. It's a little less, more in several thousands, but you're right, thousands Celsius or Kelvin. And so if you look at those temperatures, they're really high, thousands and thousands of Kelvin or Celsius, as it might be in between. Now, there's something really strange that the scientists discovered. They pointed their telescopes to the universe, just the universe, looked at the radiation coming to their telescopes, and in that way they could figure out the temperature of the universe. Any guesses on what that might have been? What do you think is the temperature of the outer space that you see around you? Guesses are good. Okay, let me tell you. Well, actually guessing is great. Oh, that's very close, okay? That's very close, though, you know, you can get closer and closer and closer. Compared to everything that I was talking about, it's very close. It was 3 Kelvin, okay? And 3 Kelvin is ultra, ultra low. It's lower than anything that we have here on Earth, okay? And so just keep in mind that the universe itself is an extremely cold, cold object. And of course, there are sparks of high temperature objects like stars in the universe, but for the most part, it's actually a very cold object. Okay, now that we have a really good understanding, or at least a reasonable understanding of what temperature is all about, let me tell you about the cold temperature world, which is where we were headed. And it was very important to actually know about the concept of temperature to understand all this. And let's go back to our actual demonstrations, and this one is going to be a fun one, okay? So if we look at this thing here, I have my good old nitrogen again, liquid nitrogen, and is the camera on there? Okay, one thing I can look at is, for example, this one is oxygen, okay? This is oxygen in here, and this is a pressure gauge. Remember that the pressure of a gas actually has a lot of information about its temperature. Now what I'm going to do is I'm going to dunk this oxygen gas into liquid nitrogen, okay? Any thoughts on what might happen there? The pressure is going to decrease because you saw that the temperature and the pressure were closely related. Let's actually try that and see what happens, okay? There's a lot of boiling out here. Can you see that? Okay, so you can see that the pressure is dropping, and let's just watch for a little bit. Boom, okay? You saw that the pressure all of a sudden went really low. Now, let's look at, and I'm going to ask you in a second why that happens. Now I have another gas here. It's called helium. How many of you have heard of helium? From where? Helium balloons, absolutely. So this is in some sense a helium balloon. And now what happens? Again, it's going low. Do you think it's going to go plummet down like the other one? No, great. Yeah, you see, it doesn't actually plummet down. It goes somewhat, it's fine. It doesn't do anything drastic. Why did that happen? Why did the oxygen pressure suddenly plummet down? Yes.
Did it turn to liquid?
Yes, it turned to liquid. Would you like to see the same, this guy here? Yes, okay, okay. He's happy. The nice thing is he doesn't become sad, okay, worry. Look, he's happy here, and what's going, it's filled with air, okay, air has some, what is air made up of? What is air made up of? Yes. Oxygen is right. What other compounds? There. Nitrogen, okay. So what's going on is he's completely deflated by this whole experience, okay. And what's really cool, there is a little bit of liquid in here, okay. And so what really happened is, as some of you said, oxygen actually liquefies, and that's really what you see happening out here. Now, so remember that there's oxygen gas. At a particular temperature, it actually turns into a liquid. And now what I can do is I can take, for example, this bag of water here, okay, and I put this into liquid nitrogen, and what is going to happen? It's going to freeze, exactly. So all of you have seen that. I don't have to tell you, you can do this at the refrigerator, except that it's pretty dramatic with liquid nitrogen. And you can see that it's actually parts of it are getting pretty frozen. Okay, what was happening out here is actually an example of something called a phase transition, okay? So what you saw were instances of what are called phase transitions, and that's a very important concept that you see in the world around you. A lot of the devices and machines that you see around you actually use this sort of concept, but it's also, as far as physics goes, if some of you go on to studying physics, this is a beautiful and important topic that you'll be studying about. So we saw that this can turn to liquid, it can turn to a solid, okay? And you saw from the pressure that you saw suddenly drop, it's a very dramatic transition that happens. Okay, so this is a very dramatic thing called a phase transition, not something which is kind of ambivalent. Should I become liquid or not? No. It says, I'm becoming a liquid right now, boom. Okay, so it's very dramatic, and it's an example of what's called a phase transition. Okay? Now, essentially, a phase transition is something where the whole internal structure, in a way, changes. And if you look at what's going on here, particularly here, if you look at the liquid to solid transition, what is the difference between a solid and a liquid? Yes.
A solid has its atoms better than a liquid.
That's very important. The solid has the atoms packed closer together than in a liquid. What else? That's very important. Yes. It's rigid. In fact, that's what defines a solid. You can look at the rigidity. Anything else? The cartoon that you have here. If you look at this versus this, what is the difference? Yes. Particles are moving more, absolutely. And what else? Structure, exactly. So the very important change that took place is that this, in a solid, the atoms or the molecules are very regularly arranged, while in a liquid, they're actually more. Usually, when you look at a phase transition that you can get as you cool down in temperature, you usually go from a state of complete disarray and disorder to something which is actually very regularly spaced, okay, or is in some way ordered. So usually, as you change the temperature and go through a phase transition, you go from a state of disorder to a state of order. It's usually true of most phase transitions. Another really good example of a phase transition is a magnet. Magnet, you can find that, let's say you take a piece of iron, heat it up to a very high temperature, it's no longer a magnet. On the other hand, as you cool, once again, a sudden change in phase transition into a magnetic state, okay? So these are phase transitions. When we go to still lower and lower temperatures, what kind of phase transition do you think happens? You saw it right, and now I'd like all of you, hopefully, to tell me, what was this thing here called? Exactly. Can I hear it again? Okay, great. So essentially, as I go to lower and lower temperatures, and let's talk about what low means in just a second, we get a really exciting state of matter. It's something called a superconductor, and that's what we're to, and we're almost there. Talk about phase transitions. That was a very important part of understanding what superconductivity is all about. And what I'm telling you is that as you go to lower and lower temperatures, you come to this new state of matter, which is a superconductor, which is very different from the kinds of, ice, solid, liquid, those kinds of materials that you see in your normal life, okay? Now, what does low mean? Let me just tell you what low means. When I say low temperature, it really depends on the particular substance. So if I look at if I look at aluminum, low would mean 4 Kelvin, let's say, really, really low. for YBCO that you asked me about, low would mean 77 Kelvin, for example, or 90 Kelvin. If we're looking at life on Earth and how long that, what temperature range that lasts, low would mean, let's say, 200 Kelvin. That's already way too low. But just to give you an idea of what temperatures we're talking about, liquid nitrogen is 77 Kelvin, and that's about the coldest we have here today. It's super cold. You wouldn't want to put your hand in there. Helium that I had, that actually becomes liquid at 4 Kelvin, which is actually way, way, way lower and become a liquid. Now, floor of this building, there's the lab of Brian DeMarco. He's doing some beautiful experiments on solidity, which is related to superconductivity. And there, they go to 100 nanokelvin, okay? And in most parts of the universe, I told you the universe is about 3 Kelvin. You don't find this kind of temperature. It's extremely low. So if those of you that are interested, you can find out about the kinds, or I can tell you a little bit more about the kinds of real fascinating experiments that are going on. And if anyone asks you what is the coldest place in Urbana, it's Brian DeMarco's lab, okay? Okay, and we wouldn't want to go into his experiment. It's totally freezing out there. Okay. Now, let's come back to the superconductor. The superconductor happens even at about 4 Kelvin, which is still extremely low, and a superfluid is also a related phenomenon. And let me actually look what the properties are. Let's actually try to find out what it is that caused this magnet right at the beginning of this lecture to actually levitate, okay? And we're almost there, and once we have the answer, it is something that you can take home, something new. Okay, so what are the properties of the superconductor? Okay, so there's 2 very important properties. One important property is that as you cool the temperature, suddenly there is a transition. What kind of transition is it? Yes, it's a phase transition, and the phase transition is actually into a superconducting state, and that is characterized by 0 resistance. So if you were measuring the current, going through the superconductor, you'd find that the resistance would just suddenly plummet and go to 0, okay? And it's a phase transition. It happens very rapidly. For the YBCO, it happens at about 90 Kelvin, okay? And what does 0 resistance mean? It actually means moving with no friction. That's a very rough way of saying it. It is something that you've actually seen in the winter world. Where have you seen a friction-free place? Louder? Ice. Okay, so ice skating. You've all gone ice skating, and for example, here there are these blocks of dry ice that I have. And if you look at this, dry ice is the substance that I have here. And you can see, can you all see this? Okay, so you can actually see that. Erica, can I just push this all the way out? Is it okay if it goes out there? It's okay? Okay, so you can see that it actually goes with friction. It breaks too. Okay, superconductors do that as well. This is not superconductivity. It's just a demonstration of what 0 friction means. But superconductivity has associated with it this kind of friction-free behavior, okay? Now, another extremely important thing, which actually is the definition of a superconductor, is that it does not allow any magnetic fields to go into it or to penetrate into it. And that's exactly what you saw happening there, which gave rise to the levitation, okay? And so essentially, a superconductor is what's called a perfect diamagnet, okay? And a diamagnet is something that actually completely repels all magnetic fields, okay? And now, this is the last piece of the puzzle. To really understand why you have levitation taking place, you actually have to understand how currents and magnetic fields are related to one another, okay? So, first of all, any thoughts on if I had a beam of electrons And in fact, some of you, several of you, in your living room have devices. You have a device in your living room that actually shoots out a beam of electrons. Anyone know what that might be? An old television. These days, several of you don't have those kinds of televisions anymore, but here we have an old television sitting out here, and here's a very powerful magnet, okay? And so we can watch a little bit of TV. It's the sort of thing to do on the weekend. Okay, and can you all see this? Can you see what's going on TV? It's not really important. There's some woman selling something. That's not important, okay? But can you see this image here? Okay. Now, what happens if I have a beam of electrons? And so what's going on is your TV, this is something that's called a cathode ray tube, okay? So you have a beam of electrons that are actually being shot out at the screen, and depending on where they hit, they actually light up one little spot. That's what's going on. What happens to electrons in the presence of a magnetic field? They change direction, okay? And so all these lovely products that these lovely ladies are selling here, we can actually do something to them by bringing this magnet close, okay? And so you can see, okay? So if you don't like what they're selling, yes? Yes. Oh, by the way, please don't try a lot of the things that we're doing here, okay? Especially putting your sibling into liquid nitrogen. Don't do that. Okay. Okay. Let's see. All right. Okay. So the important thing is that magnetic fields actually cause beams of electrons to change their direction, or in other words, a moving electron feels a force in the presence of a magnetic field, okay? And this is something, and in particular, there's something very special. There are two, I don't know if you've actually studied it in your classes, there are two laws that go by the name of Faraday's law and Lenz's law. What they tell you is that if you have a ring, for example, let's say you have a ring like this, and it's a metal, or suppose it is a metal, there are electrons that can actually go moving around in this metal in principle. Now, what you can do is you can actually apply a magnetic field, but change the magnetic field. So what you can do is you can take a ring and you can take a magnet close to it, okay? And what the changing magnetic field does is that it sets up a current in the ring. So what really happens is that if you had a ring which was a metal and you changed the magnetic field going through the ring, that would actually cause the electrons in this metal to start moving. Now, moving electrons actually do something very strange. If you have electrons that are moving, what do? They carry a current. What else do they do? Generate a magnetic field. Okay, so there are two steps to the process. One is you and change it. That causes electrons to move. Now, you have electrons that move, and they, in turn, produce their own magnetic field. If you look at the magnetic field that they produce, they actually do this to try and counteract the original field. Okay, this is something called Lenz's law, and actually it's used in a lot of, so this kind of principle, by the way, where do you think you actually have a changing magnetic field producing a current? Where have you seen that before? Generator. In fact, a lot of the current supplies that you have, all the power that you're getting, is actually coming from this kind of phenomenon where you have a magnet and you have something, for example, that is feeling a changing magnetic field that produces a current, and when you look at your AC supply, that's actually how the power is even generated. So it's pretty important. Okay, but as a consequence of this, what happens? As a consequence of Lenz's law, what happens, okay? And let's actually explore that. This is what's called an electromagnetic cannon, okay? So as the name suggests, there is going to be something quite dramatic happening. Here is a metallic ring, okay? And here is a magnet. And when I press this button, it actually induces a pulse of a magnetic field. And so what ends up happening is if there's a sudden magnetic field that goes through this ring, what happens? Louder? Exactly. It induces a current that goes around like this. Now, this induced current, what does that do? It induces its own magnetic field that tries to counteract the magnetic field that originally caused it, and as a result, it feels this repulsive force that makes it do what you will now see, okay? This is a ring, almost, but not quite, okay, because it's got a little notch in it. And now, close your ears. No, I'm kidding, it's okay. What happened? Exactly, okay? Nothing happened, and that's a bit of a letdown, but don't worry, there's more to come. Nothing happened because there's a notch here, so the circuit isn't complete. On the other hand, take this now, and what do you expect to happen? It's going to shoot out, okay? Not bad, but we can do better, okay? What we can do is we can actually decrease the resistance of the metal. What is a good way to decrease the resistance of the metal? Cool it, okay? So that's exactly what we can do. Is this where I cool this? Okay. So we can cool this for a bit. That's going to decrease the resistance of this metal, and so the effect is going to be pretty dramatic, okay? We're going to try to shoot for that, but I almost am positive it won't do that, okay? But let's try. Bubble, bubble, toil and trouble. Cool it with baboon's blood. No, it's not baboon's blood, though. That's Macbeth, by the way. Is it done? It's still bubbling. Okay, it's almost, okay, it's quietened down. It's very important to keep it quiet and spring the surprise on it. Uh-oh. All right. Okay. So definitely, thank you. Definitely, which is the one that was really good? Was this the one? Okay. When we were trying this, we really were aiming for the trash can. Let's see if this works, okay? Thanks. All right. Thanks. Okay. So that's Lenz's law for you in action. But you know what? There was some purpose to it. Actually, most of it was entertainment, but anyway, but the other purpose is that this was really to demonstrate what the superconductor was doing. And essentially, there's a small difference between what you saw here and between what you saw here and what the superconductor was doing. Okay. The only difference is that a superconductor metal is a perfect diamagnet. The metal didn't like a changing magnetic field. The superconductor didn't like magnetic fields at all, okay? And just the way the ring got repelled from the magnet gets repelled from the superconductor. So what ends up happening is that here's the magnet. There's a magnetic field it's producing. This superconductor doesn't like magnetic fields at all, and it actually produces a kind of counter-magnetic field, and as a result, that repels the magnet, and that's what causes this magnet to levitate. How does the superconductor actually produce the counter-magnetic field? It's exactly the way the metal does it. How does it do that? What causes magnetic fields? You just told me that a little while ago. What causes magnetic fields? Moving, oh, there we go. Guesses are good. Anybody, what causes magnetic? Okay, electrons is the key. So you saw that moving electrons exactly, well, line up in a sense. Actually what they do is move. So what you have is, here's the superconductor. There are these circulating currents going around, just like in the ring, and they produce a magnetic field, and that repels the magnet sitting on top. And that's how you actually have levitation taking place. Okay, so that, in a sense, tells you some of the properties of superconductors. If you really wanted to know the physics behind it, I don't have time, and you probably don't have patience today to learn about really what's going on within a superconductor. But to really learn about it, you really have to understand the dance of the electrons going on inside the superconductor. And the theory that actually explained it, or at least in low temperature superconductors, was called the Bardeen-Cooper-Schrieffer theory, or BCS theory for short. And it was formulated in Urbana. So Urbana is actually very famous for formulating this theory, and in fact it won a Nobel Prize, okay? And this gentleman here is Bardeen, who was actually a professor here, and this is the Bardeen quad. How many of you have actually seen the Bardeen quad? Okay, so those of you that don't know where it is, it's by the engineering buildings out here, or maybe out where? Out here, okay? So you can go follow it there. You'll find the Bardeen quad. And if you look at the plaque that you see, it was actually awarded to Bardeen for this theory out here, okay? So you can go and read the plaque. It tells you about the theory of superconductivity. And I'm going to finish in just a little bit, but for those of you that are actually staying on here, your reward is you'll see another rather spectacular demonstration, okay? So we've talked about superconductors, and one thing is you've seen where do they actually occur. You've seen them in the laboratory setting, or at least this is how it would look like in some labs perhaps. Another really important thing is that you see that they're ultra sensitive to magnetic fields, and so they are fantastic detectors of small magnetic fields. A really important use of superconductivity is actually in medicine. There's something called magnetic resonance imaging, which happens at the Beckman Institute here, where you can image your brain, and that device actually requires using a superconductor. And then coming back again to the universe, are there instances of superconductivity given that it's very low temperatures? We haven't seen any evidence directly, but there are suggestions that the cores of certain types of stellar objects might actually have superconductors in them, okay? So that brings me more or less to the end of my talk, except for a few things that I still have left. But one thing that you've seen is that the low temperature world is something really spectacular, really beautiful, and really strange. And in fact, we are still trying to understand it as scientists. There are a lot of unsolved mysteries. This one is in some sense a solved one. Actually, this yttrium, barium, copper oxide, we still don't know how exactly it superconducts. That's $1 million question. So there's a lot that we still need to explore, but you've gotten a little for it. And before you go back out cold, I'd like to actually come back to room temperature and a little bit of warmth and show you this final demonstration. It's entertainment. But before doing that, I'd like a hand for Erica and her elves, wonderful students, and Marion and Bernie, because they really did a wonderful job with the demonstrations. Okay, so just a little demonstration for you to take home. And let's actually heat up the temperature a little bit here. This is a blow dryer, and you can come back and ask me about the physics of it, but essentially it's a hot air balloon to get you back to some warmth, okay? Am I holding it right? Yeah. high. Is it ready to go or not yet? Maybe a little bit more. I guess we can. So that's all, folks. Thank you.